One of the most amazing and fascinating things which you can get in science, apart from time travel, is human invisibility. In fact, human invisibility as a fictional characteristic trait is so popular that we have many books written on the subject. We also have many movies made upon human invisibility. One of the first books written on invisibility was The Invisible Man, written by H.G. Wells in 1897, where he has shown how an eccentric scientist consumes lots of drugs and chemicals and becomes transparent. He becomes invisible as a sheet of glass. Then later on, he struggles all throughout his life being invisible. Well, this is all just fictional. This is science fiction. But the actual question is invisibility actually possible? And it is this question which we are going to answer in this very video. In fact, recently a paper was published in physicsworld.com where physicists have carried out actual experiments and they have recreated a quantum phenomena called polyblocking, which was predicted about 3 decades ago. As you can see, the title says polyblocking is spotted in ultra-cold fermionic gas. And it is this quantum phenomena which makes the area for quantum invisibility. Invisibility at the quantum level, at the scales of elementary particles which do not obey the laws of classical physics. Now, before we go upon learning about this quantum phenomena of polyblocking, we first need to understand various principles about elementary physics and elementary particles, various different laws which govern these elementary particles. So you see, our universe is made up of lots of particles, and we can categorize these particles into 2 groups depending upon their quantum mechanical spin. So this is the standard model of elementary particles, and this standard model includes all those particles which we know of till date, and we have information about these particles, including the recently discovered Higgs boson on the extreme right. Okay, so as I said, all these particles can be categorized into 2 different groups, the fermions and the bosons, depending upon their quantum mechanical spin and their quantum mechanical properties. Now you see, fermions are those elementary particles which make up visible matter, like you, me, and all the other things. Fermions are these 12 particles. Now bosons are those particles which carry forces, which make different forces like the electromagnetic forces and the weak and the strong nuclear forces. And these are these bosons. Now you see, the fermions are those particles which have something called a half-integer spin. Now a spin is actually a property of any elementary particle which it undergoes under a magnetic field with a magnetic current. And we have a mathematical entity for this spin of a particle which is called the G factor of that elementary particle, also known as the gyromagnetic factor. Now you see, the G factor or the gyromagnetic factor for fermions is usually in decimals, in half integers. So they have mathematical values like 1 upon 2, minus 1 upon 2, 3 upon 2, and so on. But for bosons, we have something called a full integer spin, and they have mathematical values for the spin like 1, 2, and so on. They have full integer. Now, these fermions can further be classified into 2 groups, just quarks and leptons. Now, quarks are those particles which make up composite particles like protons and neutrons, while these are all the quarks, the up quark, down quark. In fact, a proton is made up of 1 down quark and 2 up quark, and a neutron is made up of 2 down quark and 1 up quark. Then we have the leptons. The leptons includes particles such as the electrons, muons, tauons. Then we have different types of neutrinos, electron neutrinos, muon neutrinos, and tauon neutrinos. Okay, so for this part of the video, which relates to quantum invisibility, we need to focus on an electron.
So all of us know that an atom consists of protons and neutrons in its nucleus, and we also have electrons revolving around the nucleus in different shells like K shell, L shell, and so on. But the thing is that the theories of quantum mechanics and the quantum field theories tell us that you can never accurately tell the position of any elementary particle. So you can never tell the actual and the accurate placement and the position of that particle. And the reason being is that these elementary particles do not obey the laws of classical physics. So there is uncertainty in the position of such particles as well as uncertainty in their momentum as given by Heisenberg's uncertainty principle. So clearly this system of K shell and L shell needed to be refined. That is why physicists came up with the concept of subshells, as we know them today by S subshell, P subshell, D and F. These different subshells have different numbers of orbitals. Like the S shell has 1 orbital and the P subshell has 3 orbitals and so on. And we can calculate the energy of these different orbitals in a subshell by adding different quantum numbers. And these quantum numbers are the solution to Schrodinger's wave equations. Now we have two different types of quantum numbers: principal quantum number and azimuthal quantum number. Principal quantum numbers are those 1 to 4 quantum numbers which help us to describe an electron state, while azimuthal quantum numbers are those quantum numbers which help us to determine the shape of a particular orbital in a particular subshell, as well as the angular momentum of that particular orbital. All of these orbitals in a particular subshell have the same shape and the same angular momentum. Okay, so we discussed about these different types of quantum numbers as well as these different types of subshells. So what is next? Well, you see, a particular orbital of any subshell can accommodate a maximum number of 2 electrons, not more than that. So an electron actually also has this property of quantum mechanical spin. In fact, an electron has 2 different types of spin, an upspin as well as a downspin. So after the discovery of these quantum numbers as well as these subshells, physicists were curious to know if, for example, we have 2 electrons paired up in a particular orbital. So those 2 electrons will be of the same spin or will be of the opposite spin. That was the curiosity of physicists. And this curiosity, this problem was solved by Wolfgang Pauli, an amazing theoretical physicist, in 1925 with his amazing principle of Pauli's exclusion principle. So this principle stated that no 2 electrons with an identical set of all quantum numbers can accommodate the same state within a quantum system simultaneously. Now basically what it meant was that if you have 2 electrons which have an identical set of all the quantum numbers, which have an identical set of azimuthal quantum numbers as well as principal quantum numbers, so those 2 electrons should be of the opposite spin. They can never be of the same spin. So if 2 electrons need to be paired up, they always have to be of the opposite spin, not of the same spin. And this is quite an important principle because it helps us to understand the stability of an atom as well as it helps us to understand various different quantum phenomena related to an atom. It makes an atom stable as well as allows the atom to not just spontaneously collapse, releasing a ton of energy. So in fact, this principle, Pauli's exclusion principle, is the backbone of polyblocking, which is the quantum effect. So now let's come to polyblocking. All of the previous knowledge was just to create a base. So polyblocking, it's a quantum phenomena. You see, any atom which, when excited by photons carry light, which are electromagnetic forces. So any atom which is excited by photons, so the electrons in the outermost shell of that atom get excited to a higher energy orbital. And when those same electrons come back to the ground state, they release the extra energy also in form of electromagnetic radiations or photons. And that's how we are able to see something, because something scatters light. And this is the photoelectric effect given by one of the Einstein's paper in 1915. So any atom, when excited, it gives off light, it scatters light, and that's how we are able to see it. But things tend to get changed when you cool down an atom to like crazy low temperatures, just touching absolute zero, and under intense high pressure. Because in these conditions, what happens is that the atom loses its energy, and the electrons, the outermost electrons in that atom, are constantly jumping to the lower energy state, to a lower energy orbital. And there comes a temperature, a very low temperature, at which all the electrons in a particular atom are at their lowest energy state as possible. From then on, they can neither jump to a higher energy state, nor they can go back to a lower energy state, even by being affected by photons. So light is not scattered in this case by the atoms. Light just passes straight through the atoms, thus giving us this beautiful effect of Pauli blocking or quantum invisibility, because light is not being scattered, and thus the light just passes straight through in form of photons, because the photoelectric effect is not occurring in such cases. And this is what makes it special. In fact, this paper tells us that the researchers, they first did with the experiments with lithium 6. So what they did was they took lithium gas in a complete atomic chamber, and they used laser cooling to cool that lithium gas, and then put it under a ton of pressure, and then they passed the blue light through them, and the light was not scattered, and we got the phenomena of Pauli blocking, quantum phenomena with quantum invisibility. Then it says that then the researchers in New Zealand did it with potassium 40 fermionic gas. Fermionic gas is like the same gas when you do all the things with it, like cooling it down to very low temperatures. And they cool all these gases to like just microkelvins, which is just above absolute zero. Then they also did with a gas made of rubidium-87, and they also cooled fermionic lithium-6 atoms. And in the case of lithium-6, the transparency increased a bit more. So this is what quantum invisibility is, or if you like to say it, Pauli blocking. Now, according to this article, I guess invisibility is possible, but at the levels of quantum mechanics, at the level of elementary particles. But who knows, maybe in the future we accomplish human invisibility, and that would have been even more interesting. So I guess it's kind of wrong to say that invisibility is not possible, because it is at the level of quantum mechanics. Thank you.